Okay, so here's what we've got today.
Just to get it out like that.
We're gonna finish up this lab, and hopefully then collect all
I
the
should
data
do
that I
that
tell
now.
you to do in a timely manner.
I'm just a little.
Collect all of the data, yeah. Anyway, so here's what I want you to see, okay? So you all took the block and you pulled it at a constant velocity, okay? So, and I've told you this before, but the sooner you understand this concept, the easier the forces unit is going to be. Every force problem only has two options. Either the forces add up to equal to zero, and we say the system is in equilibrium, and you have a constant velocity. And that constant velocity might be zero, it might be 10 meters per second, doesn't make any difference. But as soon as you see the words constant velocity, just make all the forces add up to equal to zero. You don't have to make them add up to pi or like negative 99. Zero. This is it. Okay? Or if you see something moving at a constant velocity, you know the forces add up equal to zero. So if you're driving your car and you set your cruise control at like 40 miles per hour, and you're driving in a straight line at 40 miles per hour, no matter how complex the system is, if you're moving in a straight line and your velocity vector isn't changing, either speeding up, slowing down, or changing directions, all the forces acting on that system add up to equal to zero. That's it. Now, if you see accelerated motion, and you see something speeding up, slowing down, changing direction, there has to be an imbalanced force. Okay, that's it. Those are the only two options. Okay, and if there's an imbalanced force and you're going to accelerate, what are the only two things that can happen? You either
Speed up.
or slow down. Okay, eventually we will change directions, but that's another unit. Okay, but for now, we're only going to be talking about magnitude. So the next two parts of the lab that you're going to do today are examples of both of those. The first one, and we'll show you this, but you're going to have a force table, and you're going to have some weights hanging from strings so that the system is in equilibrium. Okay, great, the system's in equilibrium. What do all the forces have to add up to?
Zero.
Zero. And when you drive them in the tip-to-tail method, where should you end up?
Zero.
Back at the origin. That's it. Okay? So no matter how complex the system is, make the observation. Constant velocity, accelerated motion. Now, in contrast to that, you're going to take a ramp, and you're going to take a string, and you're going to tie a weight on the end of it, and you're going to let go of that, and you're going to drop the system. Okay, you're going to let go of this. You're going to put a weight on the end of it. There's a string with a pulley. Boom. What do you think the cart's going to do? Accelerate, because now you have an imbalanced force. So the gravity mafia is pulling down on that weight, and it's going, yo! Big Tony is going, you need to cut down here. We need to talk. Okay? So Tony is beckoning you. And not only, so this thing has to go, plus it has to drag the cart up there with it. So in that situation, you're going to have an accelerated motion because the forces aren't going to add up to equal to zero. With force table, the forces are going to add up to equal to zero because the system is in equilibrium. Now, there's a common misconception. When you look at the block that was being pulled, and you had force applied, and you had force friction, and you had Fg, and you have force normal, okay? So, when you talk about Newton's third law that says for every action there is an equal and opposite reaction, okay? This is not it, okay? Force applied being balanced out by force friction, that is not Newton's third law, okay? It's not Newton's third law. Newton's third law comes in right here when you're pulling it. So when you pull on that block, the block pulls back on that with an equal and opposite force. But this in kind of, so I just don't want you to think, oh, this is Newton's third law. Newton's third law is happening at that interaction. When I drop this weight, okay, gravity is obviously pulling down on the weight because of the earth. So the earth pulls down on the weight. Well, by Newton's third law, the weight is going to pull back up on the earth with an equal and opposite force. This has a lot less mass, therefore this is the one that accelerates. The earth technically does accelerate when I drop this, but it's like 2 point something times 10 to the negative 23rd meters per second squared, okay? You can calculate it. Is it really going to do that to a measurable degree? No. All right, so let's talk about the two diagrams that I want. And I think I glanced at Collins and that looked pretty good. So the first one is going to be this free body diagram, okay? So as we begin to get into forces, forces are a very visual unit, probably the most visual unit that we're going to have. And if you come up to me and you say, hey, Burkamp, I don't know how to do number 5. Here's the first question I'm going to ask you. Have you drawn all the forces acting on the system? And if you say no, I'm not going to help you, okay? And I'm not doing that to be a jerk, is because literally, if you don't know the forces acting on a system, you can't begin to solve the problem. Now, if you say, Burkamp, I don't know what the forces are, that's a whole other ballgame, okay? And then it's like, okay, hey, let's figure out what those forces are. So, when you look at that block, there's 4 primary forces: gravity, the normal force, your force applied, and your force friction. So, your first diagram is going to look something like this, okay? Should look like a big plus sign. I want to see what scale did you use. Did you let 2 centimeters equal a Newton? What did you choose for that scale? And every one of these better be labeled, because if you just draw random arrows don't mean anything. Okay, I have no idea what random arrows mean. You should have 4 of them labeled. That's what the first diagram is going to look like. The second diagram, you're going to draw that tip to tail. I always draw my gravitational force first. Force normal, boom. That's what the second diagram is going to look like, okay? So diagram number 1 is going to look like a plus sign. Diagram number 2 is going to look like a rectangle. Only draw it for the wood-on-wood system and the constant velocity one, okay? I don't need to see all 8 experiments. I just need to see the wood-on-wood constant velocity. Again, make sure that you label those vectors. Now, part 2, which some of you did not do. So,
Actually, I blame Danny. Let's blame Danny.
What?
Yeah.
That's
It's Danny's fault.
That's
okay,
Okay.
Okay.
so you took a 200-gram mass, which is 0.2 kilograms. Now, here's the story. There's 2 ways I could figure out the weight of a 200-gram mass. Option number 1, I take a Newton scale, I hang it up. Boom. It should read 1.96 Newtons. The other option is that if you know the mass, and this is going to be important when you do like the force table lab and the second lab that you're going to do today with the colloids, you've got to be able to say, oh, great. Gravitational force is always mass times the gravitational acceleration. So you can take 0.2 times 9.8 meters per second squared, and you're going to get 1.96 newtons. So you're pulling the block. So Cohen, what was the weight of your block?
3.9 newtons.
Exactly, 3.90.
Yep.
Yeah.
Make sure that you're consistent on how you write down that data.
360.
So if I'm Cohen,
I'm sorry for your loss.
yeah, no kidding. I could be worse. So I got 3.90 newtons and 1.96 newtons. I'm going to add that together, so the total force that I'm going to pull is 5.86 newtons. Okay? So what you're going to measure is how much force it takes to pull that thing at a constant speed. Okay? So let's say that was 1.20 newtons to pull it. Now, here's what you have to understand. We don't directly measure force friction. What we measure is how much force it takes to pull it. So if we know how much force it takes to pull it, then we know how much we're paying to the frictional mafia. Okay? So you're pulling this thing along, hey, it takes you $1.20 to pull that lock. What that means is that the frictional mafia has said, hey, you want to pull this system, you got to pay Tony $1.20. Okay, that's it. So the other thing I want you to understand, and this is a bigger picture, is that the only reason you have to keep applying that force to keep that system moving is because there's friction. Okay, that's it. That's it. There's friction. If that was the magic frictionless block, and we have the magic frictionless table, you'd have to apply a force to get it to move, but after that, you could let go of it, and it would just keep moving across the table. So whenever you have to apply a force to keep something moving, it's because there's friction. So get out of this mind, your Aristotelian view that says, oh, the preferred object, motion of an object is to come to rest, okay? The only reason it comes to rest is because of friction. Mother Nature could care less. Mother Nature goes, hey, and you're moving, you keep moving. If you're at rest, you stay at rest. But the frictional mafia says, nah, Mother Nature, we really like things to come to rest because that's how we get our money. So Mother Nature and the frictional mafia have kind of come up with an understanding. Mother Nature goes, hey, if you're not here, I'm going to let you keep moving. The frictional mafia says, nah, I think we need the money to stop. So when you see something either stop, when you apply the force and you stop it and it comes to a rest, that means there's friction. If you push it and it keeps going, because it has inertia, it just wants to keep going. All right, so you're going to draw a graph, and you're going to put force friction here and force normal here, okay? So your force normal is just going to be, like in this situation, the 5.86 newtons. You got 1.20, so you're going to set up some scale, okay? And you're going to have some data points. Odds are they're not going to be in a straight line, okay? Should be pretty close, but odds are they're not. Now, this graph might go through 0, 0. It might not. You're just going to draw a line of best fit, okay? If it happens to go through 0, 0, great. If it doesn't, hey, it doesn't. And that's the data that you have. But again, read the instructions. I underlined it. Circle the points used and write the coordinates on the graph. I want to be able to see, hey, what points did you pick on the line of best fit, okay? That's the whole point of the line of best fit, is that you pick points that are actually on the line. Now, if your data points happen to be on the line, cool, winner, winner, chicken dinner. If they're not, you can't use them, okay? Then you're going to find the slope of that line. Now, here's the story. Unity change in y over change in x. You're going to take force friction unit and divide it by force normal, okay? That's going to represent something. So first off, when you find the slope, what units is slope going to have? No. Okay? Then ask yourself, what did we talk about that didn't have any units? That might tell you what the slope represents. Cool with that. Okay. On number 7. So here's this car, right? Now, you're moving at 10 meters per second. That just tells you that you're moving with a constant. You're just moving with a positive velocity, okay? That's all the number really tells you. Brakes are applied. The car stops turning. This creates sliding friction where mu is 0.7. Based upon this, what is the frictional force acting on the car? So here's the story. So you're moving at 10 meters per second and you hit the brakes. In terms of velocity vectors, what is the function of brakes? To make them bigger or to make them smaller?
Smaller.
Smaller. So you're going to begin to slow down. Are you going to begin to accelerate when you hit the brakes?
Yes.
Yes. And if you were to draw a velocity time graph, this velocity time graph would do something like this. You're going to start at 10 and you're going to go to 0. I don't care about the time, not part of the story. Okay? Literally, the time is not part of the story. But here's the main point. What's going to be the sign of the acceleration?
Negative.
Negative. Again, I don't care what the acceleration is. I just know that what I need to understand is that there's going to be negative acceleration. Now, Danny, that big sign behind you, F equals ma. If I have negative acceleration, which I'm going to, what's going to be the sign of the force then?
Negative.
Negative. Now, the question is, what's the force that's going to make the car stop? Right now, you only have 4 forces you can choose from. Is it gravity, the normal, the force applied, or the force friction? Force friction. Oh, that's what's going to make the car stop. Okay? That's what's going to make the car stop. So, then you go, oh, how can I calculate force friction? Well, you know that force friction equals mu times force normal. And there's an absolute value sign around that. So I've given you mu. You have to figure out what the force normal is. How are you going to get your force normal? Well, force normal is the same thing as what? On a flat surface.
Gravity.
Yeah, the pull of gravity. You know the mass. You know Fg, which is going to force normal, is mg. You got the mass, multiply that by g, boom. There's your normal force. Multiply that by the coefficient of friction. There's your force friction. Now, here's what you want to ask yourself. In the context of this problem, allowing for what Danny said, when you write down the value of that force friction, is that going to be a positive or negative value? Colin, think this through.
It would be negative.
Car is moving with a positive velocity. If you apply a positive force to it, what are you going to make the car do?
Accelerate.
Speed up or slow down?
I just looked at the absolute values.
That's why I said, yeah, your absolute value is going to generate a positive value. But then you have to look at it in the context of the problem. Okay,
Your car approaches a pedestrian. You
Over
slam
on
the brakes and
page-
speed up.
2. Okay? When you read number 8, you got a mass, 950 kilograms, moving at 15 meters per second, brought to a rest in 20 meters. Find the acceleration. What value do you not have on number 8? What is missing?
Coefficient.
Well, beyond that. Time. You don't have time and you need to calculate the acceleration. So what equation are you going to use?
That equation.
That equation. Once you find the acceleration, then you can use F equals ma, then you can find the force. Once you have the force friction, then you can calculate mu. On number 9, when you read number 9, what are the 2 most important words in all of number 9?
Constant velocity.
Constant velocity. What do all the forces add up to? 0. Okay. Keep that in mind. Okay. Bring the labs. Let's go to the back room and I'll show you the next 2 parts. So, Cohen, stop yonder.